Okay. Good morning, everyone. So there's a bunch of people who also helped to prepare what I'm going to present today. Because I started working in the 2000s, I started by being a web developer, right? And I've migrated to full stack. Now, lately, on par with my academic track, I've also doing some consultancy for a bioinformatics company on AI. So I'm going to share a little bit about what's going on and what this has to do with custom programming languages. So I want to do this a little bit more interactive. So is there a mic? Can you pass it? Well, not you, because I've heard you today, but can you pass someone? Can you tell me what AI is?
No.
No? Do you want to give it a try? We know you know, so.
Not sure. I mean, AI is supposed to sort of represent how humans think, but make the machines do it.
Okay, I'm sorry, you are in my group. So if you ask a scholar, that's kind of what they will say. You want to achieve human level reasoning using machines, kind of in the lines of what you said. And what academics think about developers is that it's a bunch of bullshit. You just use it as a marketing term to get some VC-backed money. Now, if you do the other way, developers only see AI as a way to build better products or new products that don't exist yet, right? So this is the other side of the coin. And if you ask them what scholars think, you get like something really weird, that you shouldn't use them, right? You shouldn't use AI, it's too dangerous. So this is both point of views from the other side. Actually, this was presented in the early 80s, I think 80 exactly, yes, as strong AI and weak AI. Have you heard of these terms? No. Okay. So strong AI is the one that can do everything at a human level, and the weak AI is really good at something, but can only do that something, right? And with LLMs, is the first time we're actually converging towards strong AI. Has anyone seen this challenge, the ARC or ARC Prize, ARC AGI? So the idea is that there's a bunch of data sets with 3 or 4 instances only, so 3 examples, and you need to predict what's the output based on just 2 or 3 of the top ones, right? And LLMs are actually quite bad at this. And the data set was designed so it mimics the human-like abstract reasoning that you do. That's why it's mostly geometric with colors or something that catches your human eye. Okay? So LLMs are not good at this, but we'll see some algorithms today that are actually better than LLMs. On the other way, you have weak AI as your spam filter, right? So I wouldn't ask your spam filter to write code, right? But it's reasonably good at filtering the spam. Yeah.
Didn't speak strong to weak AI, I understood if I remember so. Strong AI say that the brain is a digital computer. So I don't think it's slightly issues in the sense, or I'm misremembering it.
No, that's part of the thing, but I think for the sake of everyone else, we can leave that discussion, because it's a very interesting discussion of whether, so LLMs predict next token, whether that's what happens in your human brain or not. So I think that's the main discussion. It's about that little point that has huge impact on how you see the stuff, right? Maybe let me go with my stuff and we can discuss that afterwards. Right now, everyone wants to go into AI because otherwise they're out of a job, right? Because that's what's happening. Economy is changing. For me, I would rather still have a job and not everyone retire. I don't know if you've seen the movie, but I don't want to end up like this, right? I still want to keep practicing. So I want to adjust what I do to incorporate all of these tools. And I don't know if you read, this is a quite recent paper. So they monitor developers for a few months. And when they asked them, did you feel more productive using AI-assisted tools? They said yes, about 20% more productive, but actually they were around 20% slower than they were. So when you talk to people and you get, yes, AI is, really helps me to do things faster, you should take that with a grain of salt, right? So, sorry, I'm not selling a silver bullet. You have to be careful about all of this stuff. So it's 2025, and I think the answer to what is AI is LLMs, right? Or maybe you can consider foundation models. Or if you're doing self-driving cars, you can use DNNs or CNNs, right? So this is mostly what people mean with AI nowadays. But do you see the other ones there? Maybe let me make a little bit darker for you. A little darker, a little darker. Okay. So there's a bunch of other stuff that have been here for a long time. By the way, neural networks are from late 60s, if I'm not mistaken. So
1958.
58, right? So they have been here for a really long time. So have been other things. So has anyone here heard of Prolog? That's AI if you ask someone who was teaching back in the 60s. That's the only definition of AI back then, almost. But you have other things. So random forests or boosting models, these two are actually mostly the same thing. Up until today, if you have a tabular data set, so a bunch of rows and columns that you want to predict something, neural networks are not the best approach to do it. Boosting models still win in that kind of benchmark, right? But you have other things, and I'm going to talk a little bit about evolutionary algorithms that also been here since late 80s, 90s, but people don't look at them, and I'll show you how they might be interesting. So I was going to do a presentation mostly based on code, but these two guys, I think, they saved me from doing that because you had the Liquid Haskell tutorial yesterday. So this language is very similar. Let me, so you can see the code. You can see the code now. Okay, so in this language that we've been working on, you have liquid types, right? So this error code should be between 100 and 599. So this is a hard constraint that I put on the model. And if I ask my LLM to generate and fill this all for me, so this is code that I haven't written yet, it takes a while because I'm running LLM on my laptop, not using any cloud service, but it should be like less than 1 minute still. It will provide me with a suggestion of something to write here based on the description. And the advantage of this language is that it will verify that it's within those bounds, right? Now, if you've been, by the way, who has been to the Liquid Haskell tutorial yesterday, so I have an idea? Okay, probably half or more than half of the audience. So it gave me 404, you know it's the right answer, and it checked that it was right. Now, if I try to do something stupid, and please don't tell me that humans don't do stupid things. This will actually probably loop forever because it's generating 404 plus 200. So it's not merging the results, but actually giving a program which does the sum. And it's going forever because that answer does not satisfy the bounds that I defined, right? So I can stop it now and go back to the presentation. So I think this is what you meant when you were talking about Lean or Idris or Agda, is that you can have LLM generate code, but you actually verify that it's correct. Now, I've been writing Lean, and I don't have enough time to write Lean. Like, it's like playing a computer game in which the win is that your code compiles. So you have to go through several levels, level up, and so on until it compiles. Now, liquid types, they do this without any manual proofs. You're a little bit limited on what you can write, but it's completely automatic. I didn't have to write any proofs, and you got the confirmation that it was within the bound. And in this case, if it isn't, it goes back and forth with the LLM and tries to figure out something that works. So this is what I'm trying to sell you as a good idea. And although this is a very simple example, I will talk about some larger examples. Yeah, so this is the workshop. Has anyone read the AI Law Act? Or do you know what it is? Especially if you're based in Europe, you should. So it's a new law that constrains what kind of services and products you can sell that use AI. Okay? The UK is doing something similar. Even the US is trying to figure out what they should do, although the US doesn't like laws constraining their companies very much. And you have here a couple of things, which is if you're an high-risk system, so if you deal with health, with children, defense, citizen privacy, and a few other things, you need to comply with extra requirements. And one of them is for the output of your system, you have to prove that is correct, or you have to show why it got to that stage. Okay? So this is the main issue. Now, as far as I know, they're still hiring the people that will check that companies do this. They have a really small office with only a few people. They're increasing. But I imagine in 2 years, this will be more enforced than it is today, but it's already in place, the law. Let me maybe skip. Okay. So as I said, I did some consultancy for a bioinformatics company, and they use this neural network. It's called Place AI, but I'm guessing none of you has heard. It's actually an average of 5 neural networks. And each of these little things is a layer with a bunch of parameters, and some of them are even blocks of layers. In practice, this reduces down to 12 gigabytes of floating pointing numbers, one after the other. Are you ready to go on court and say that you trust those 12 gigabytes of floating point numbers in a row? Even if you were the one that trained this neural network, you're not sure, right? And this is a problem. So even the company that produced this neural network, they don't know what to do with that. So they can do some predictions. And by the way, what they do is they look at your genetic code and they predict for a position whether it's going to cause a disease or not. Now, to raise the stakes, they actually use this to recommend that a pregnant lady would do a medical-induced abortion because they know that the fetus will not survive, right? So are you willing to give that recommendation based on a bunch of floating point numbers that someone found? Okay, so this is the scenario. I'm sorry if I got a little bit dark. Our solution was to use one of these algorithms that it's not a popular kind, because LLMs cannot look at that network and say anything, right? There are a bunch of methods to look at neural networks, but they didn't work in this case. And our solution was to create a DSL that would try and explain what's going on. So this DSL, of course, I'm not showing you the right one. Right one is only for geneticists. I don't understand most of it. But the idea is that you can create an explanation, a program, a small program that corresponds to the behavior of the neural network on a single point. Okay, so you can explain why that prediction alone worked like that and not all predictions, because for that we would need to have something better than neural networks, which we don't. So the idea, has anyone heard of evolutionary algorithms or genetic programming in this case? A few of you. So the idea is that we create a bunch of programs, random programs, and we try to assess how good they are at the problem. And if we found a good enough, we can stop there, but otherwise we can try and pick the best two and try to combine them together to get another one. We see if it's better or not. If it's not, we can even discard it. If it's better, we keep going and try to combine 2 by 2 until we get to something that works. Of course, again, not a silver bullet. This doesn't work for everything, but it's quite good at combinatorial problems. Okay, so when you have something that when parts of them are combined, you can actually improve it, that's a scenario where you use it. And that's the case with DNA sequences, where you can try and play with them a little bit, and it kind of explores the neighborhood. Yeah, and if you want to learn more about DSLs, you can find a time machine and go to yesterday's workshop. So we found something. We found that by introducing DSLs, we were expecting to have more interpretable results, but for the performance to be worse. But we found that actually performance was also better. So our DSLs constrained what the AI could find with domain constraints that we know of, right? So this is something that if you're doing LLMs, you put these as prompts. Now, I would argue that I would rather a mathematical and logical basis for writing these constraints than just prompts, but I think it will depend on your domain, right? If you're doing high-stake stuff, I would recommend to do the formal verification path instead of just using the natural language. I don't know if any of you have to deal with clients directly, but English is a really bad specification language, right? At least from my experience. I can skip over this. Now, another thing that if you were in the workshop yesterday, you've used maybe without knowing, do you know what SMT solvers are? Or has anyone used them? Only probably an overlap with the previous question. So maybe let me give you big enough? Sorry, a lot of stuff. Not this. So Z3 is one of these SMT solvers. So this was done mostly at Microsoft, and it's production grade. They use it for plenty of stuff. And the idea is that we can create an integer x that doesn't have any value. It's an abstract integer. So in principle, it could have any value that you want. And then we can create a solver, and we can add constraints on x. So let's say that x is greater than 10, and we can add another constraint that x plus 1 equals 66, something like this. Now I can check whether there is some value to x that makes these equations possible, right? And these are very simple examples. You can, you have data types inside SMT solvers. So, and it's true, and I can even ask, give me one example. So 65 in this case is the only one. I could also say that x plus x equals 4, together with the previous ones, and if I check, no, there's no solution for all of this. So you can actually ask SMT solvers to give you a solution to an optimization problem by providing these constraints, right? And if you use liquid types or this language, you're actually using this under the hood without knowing, right? But this is another tool that you have at your disposal. Now, what we're doing is we're putting all of these tools inside the same language, so you don't need to use them explicitly, but rather the synthesis of the programs already take into consideration all of these constraints. Okay, so we have here a bunch of alternatives, and I want to compare them on on three criteria. So correctness, whether they give you what you what you want via some specification, whether they are creative or not. And again, we can discuss what creativity is later if you want, and performance. And SMT solvers are by far the fastest ones. Okay, they're really, really fast. But if you ask for a number greater than 0, it will give you 1. If you ask for another one, it will give you 2 and 3 and 4. So they are not very creative in the sense they don't provide diversity in the solutions. And for some domains, you want diversity so you can explore a design space. Let's say you're doing CAD or design or something like that. LLMs, on the other one, have very high creativity. You can even set up the temperature if you want, which we always increase temperature when we don't find something. But their performance is okay, but their correctness is very low. So most of the time it generates things that don't comply with the restrictions that I asked it explicitly to comply with. And for me, that's a problem if you're doing like critical systems. If you're just writing some web application that you can just ask something, this doesn't look right and fix it, it's not a problem. So again, you should adapt whatever you use to your own context. And evolutionary algorithms are in the middle. Their main downside is that while LLMs give you an answer in less than 1 minute, evolutionary algorithms can take hours or days. Again, not suitable for everything. You don't want to have it write code interactively. But you can leave it running during the night in order to figure out a solution to a very hard problem. And after showing you all of these 3 combinations, as you've seen, I'm not trying to sell you one of them. I'm actually trying to sell you the combination of all of them. So I think SMT solvers, and in particular liquid types, can help you when you use LLMs, and can also help you when you're using genetic programming or some other heuristic method. And the other way around, if SMT solvers are not enough for your problem, you can use one of the other 2 to complement them, right? So the title of the talk, first of all, it was a marketing bullshit, as I told you, because it's AI native, and you don't even know what AI means. But the idea is trying to combine different aspects of what people consider AI tools or techniques and try to combine them together in order to provide the developer a better experience. Okay, so that's the main point of the language. So the idea that I'm trying to sell is this, is to use exact methods to validate arbitrary code that's being generated by LLMs, by evolutionary algorithms or other methods that you might find. So another example we worked on. So this is a Super Mario level. So we had a bunch of criteria that we know that a level is good or not. And we actually wrote it in this language. So first we created the DSL to specify what is a block, what is a platform, what is a tube, and so on. And you have the constraints there in the code. And in our language, you can actually, when we want to generate a level, we leave it with a hole. And we can have constraints like minimize and maximize and other stuff. So you can ask it to generate stuff for which you don't know the right answer, right? But you can have some hard constraints, and you see them here. And you can have some soft constraints. You're just trying to do your best in this axis. And you can have as many axes as you want. This was based on some existing word, and we could just replicate it inside the language without using any special library or toolkit. So at least for us, this was a very happy moment. The other thing that we're also trying to do is AutoML. Is everyone here familiar with AutoML? Okay, so if you're doing machine learning, you get your training data, then you have to clean it up, to pre-process it, to create some features, blah, 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 and you have to create this whole pipeline until at the end you create some model, some neural network trained or something like that. But this whole process could be automated, right? And that's the idea of AutoML, is not to do this by hand, but just, here's the training data, I want to maximize this criteria, go and find me the best transformation of every single step. Sorry. So can you tell me the difference between version 1 and version 2? I can tell you that one of them is correct, the other one isn't. And just like the the researchers that we surveyed, they also didn't know, and they wrote the code. Now, you need to understand something. So we're actually splitting the data set into a training and test data set, so 70-30. That's what the train set and test set do. We're training a random forest, which is one of the most popular basic machine learning algorithms, or classical if you want. And we have line 9, which does oversampling. So the trick here is that the original data set, it's not balanced. So if you have, let's say, cats and dogs, which is the example everyone uses, it means that we have, for instance, 90% are dogs and only 10% are cats. And if you train a random forest on that, it will have a really bad performance. So random forests, they expect things to be 50-50. Do you know where this is written? Well, it could be in the documentation. But do you know who doesn't read documentation after ChatGPT appeared? Well, everyone, I would say. And most of this stuff that we found was not in the documentation, was either in a source code comment or in the original paper. Do you see people writing code, reading the papers from which the code was generated? Yeah, that's true. So the idea of these liquid types is that you can embed this extra information into the program, in which when you write the code, you don't see it. But when I wrote each of those functions, I actually encoded this behavior. So you would get this error here that I failed to prove that this train set was balanced because it came from the original DF, the original data frame, and I don't know about whether this is balanced or not. While on the first example, because I'm doing smart oversampling, this means that I will repeat the 10% over and over again until I have 50-50. Actually, the output of that function is guaranteed to be balanced. So that information gets propagated until on the train set, I know that it's balanced and it's not a type error, right? So this is a mix of static analysis and type checking, where you can actually see more things than, is it an integer or a Boolean or something else? It's actually more about the semantic properties. And I think this is the kind of power that you need when you have AI generate these lines of code, because it will not know this hidden semantics of the sequence of instructions, not just the instruction and the argument, but rather whether the sequence was correct or not. And again, this goes to the idea that LLMs are really good at predicting the next stuff, not necessarily to reason about the composition of everything together. So we actually did a tool where we had we designed the visual pipeline for data scientists to look at, and we found a few bugs. Now, depending on familiar you are with machine learning, this might be useful or not. So this was a PHP compiler, and you have a bunch of opcodes. So like the different instructions in assembly or whatever, but in PHP. And they were actually considering this to be a continuous value. And the difference is that the difference between an op and an add is not the same difference as an add or a sub. So this is the difference between discrete values and continuous values. But machine learning frameworks, they don't care about that. Everything is continuous. Even if you give them integers, it will convert to floating point numbers. So this was a conceptual bug that the authors of the paper did not know about. But after we told them, they said, yes, you are right. We should change that. The reason why we knew this is because we were writing the type annotations for the functions. So if we didn't care about this verification, we wouldn't have got this bug even without writing any code. So this was just found in an interview. So sometimes just thinking about the specification makes you find bugs without even using these tools or the language or whatsoever. So this was a really good use case for that. The other is that, let's pick up the cats and dogs example again. You have 90% cats and 10% dogs, but the data set was in order. So the dogs would only appear at the end. So when you split 75% and 25%, if you don't shuffle, you'll end with dogs only on the test set. Again, this happened in production. They were having really bad performance and they didn't know why. And the reason was just you needed a line saying shuffle in the middle of the pipeline. So just one line of code can go your performance from being 30% to being 85%. And if you use this type of programming languages with liquid types or some kind of verification, you get these errors immediately. Not after spending a lot of money on cloud to train the model and finding out the performance is really bad at the end, probably wasting hundreds of thousands of dollars in this process. Okay, so this was a particular client. The other one is similar. Is when you want to do cross-validation, which is with the same data set trying different scenarios in terms of time, you actually can't use the future to predict the past, at least in that scenario. It would be really easy to predict whether stocks would go up if you use this training data, the value from tomorrow, right? Again, when people write code, this happens. Just because they didn't use the correct flag in the function, the right argument. And this is the kind of semantic properties that we want to figure out and identify immediately when you're writing code. You don't need to run to detect these problems. I think that's the main advantage. The other point is data leakage. So during contamination check, we discovered that portions of this benchmark were inadvertently mixed into the training set. Do you know where this footnote comes from? The main ChatGPT paper. So even big companies, when they produce AI, they do this kind of contamination errors, where if you have the same instance, so the same cat, and you send it to the training data set and to the testing data set, it will be really easy to predict what it is. Because it's exactly pixel by pixel the same as it was in the training data set. That's not how you're supposed to evaluate AI results, right? But in order to do that, you need to keep track of where everything comes from. Again, that's something that you can do with this kind of tooling and liquid types in this case. Okay, so maybe I'll give you the brief overview and I'll skip the slides. So we have some partners in the US that work with the military. So I don't work with the US military directly, but they do. And the scenario they proposed to us was the US is trying to generate drone flight plans automatically. So they want some goal for the drone to be there and do something, I don't know. And they want the plan to be automatically generated. And they even want to do it offline with no device. Now, we looked at the kind of source code that is used by these projects, and and we did the same kind of analysis, and we found 4 bugs with an evening of work just adding these annotations, these extra type systems. So we found 2 on the camera module, 1 in the FTP module where you upload the mission, and 1 in the tracking system, more or less. And it didn't cost us that much to find these bugs. Okay, so this was not human. So this was not AI generated. These were humans that wrote this code. But I think if we can find the bugs there, it's even easier if it's AI generated code, because there's even more bugs to appear just because they produce code faster. I'm not saying they are better or worse, just they are faster at producing code. And we also did some study and we found a bunch of this stuff where you actually have configuration files in the robots, but documentation says that it should be between -1 and 1, and someone said it is 2. We didn't find one example like this. We found hundreds. Not as easy as this one to see, but more complex, where you have parameters that depend on other parameters and so on. So the problem is that XML or YAML or JSON files are not very good for specifying these things, because they cannot tell you that you were wrong. That value is not possible. Now, for instance, if you use TypeScript, you can even specify some of these properties, and there are other languages that allow this. I'm not trying to sell you mine. I'm just saying, look at the tools you have in your languages and try to use them to avoid people doing this kind of mistakes. I can skip over. Okay, I can show you this. So we modeled 84 real-world bugs in robotics, and in our solution to prevent them, 17% used refinement types, and 32 of the overall used dependent types because the value depended on something else that was before. Okay, so my takeaway is that you need functional programming because if you want to assess these things or these candidate solutions, you need to do it in parallel. So you need complete independence. Liquid types and other verification systems can prevent you from even running programs that you know are invalid. You can use property-based testing for extra coverage. I didn't talk much about this. And you have different alternatives for different types of problems, and you should know a little bit about each. Okay, so these are my main takeaways, and I'm happy to take questions.